everyone. So my name is Xiaoping Li, and I'm an associate professor here at USF, and I'm also directing the NICER UTC. And this is a special graduate transportation seminar that is co-sponsored by NICER, and also, this, by the way, this seminar series is sponsored by all the UTCs, and this one is featured for NICER. So today I am very glad and honored to have a very impactful and renowned scholar to present his work here. And Dr. Henry Liu from University of Michigan, and he is a role model in all measures for a successful professor. In terms of fundamental research, he's had many publications in top journals like Nature Communications and many top journals in transportation, and he's a world-class leading research expert and leads a very strong group on connected automated vehicles, traffic signal control, and as well as other areas in transportation. In terms of tech transfer, his group has published many patents, and he's involved in leading activities in a number of companies, including DD, and he's led multiple projects, including those on the order of tens of millions of dollars on deployment. And for education, his students are everywhere, including in top universities like Columbia, Purdue, RP, and two of his students got recent career awards. And he's also leading various professional activities in various committees, and also he's a director of a regional UTC with a focus on connected automated vehicles. So without further ado, I'll have him to present a very nice piece of work that I'm looking forward to on a naturalistic and adversary driving environment. So the stage is yours, Dr. Liu.
Well, thank you, Professor Li. Thank you for your nice introduction, and thank you very much for that. It's my great pleasure to present my recent work on autonomous vehicle safety testing with naturalistic and adversarial driving environment. And testing and evaluation of autonomous vehicle safety is, I would say, critical step for the commercial deployment of these vehicles. Is also attract a lot of attention from not only the AV developers, but also government agencies as well as academia. And we see a lot of research work in this field as well. However, I see very few transportation researchers working on this topic. So in today's presentation, I like to talk a little bit more in terms of why this topic is also a transportation engineering problem, and I want to be I want to present that in a transportation as a transportation problem, so that you can have a feel on it. And so to do that, the presentation today is focusing on the problem and the challenge associated with the testing and evaluation of autonomous vehicles, and rather than the solutions, although we are going to talk about some of the solutions we propose. And if you would like to get into the more details, and you can always check into some of the publications, which I'm going to list at the end of my presentation. All right, so I'm going to start with the obvious, and safety testing is obviously very, very important. And this is not only important for AV developers, as I mentioned, but also important for consumers to boost up consumer confidence on the future adoption of autonomous vehicle usage. And I also list a few of these notable crashes involved with autonomous driving functions. One from Tesla, another one from Uber, and then some of the collisions Waymo vehicles get involved with. And some of these are not autonomous vehicles' fault, but what I'm showing here is that these vehicles are still under development. They are not safe sufficiently, at least. And so there are some areas which they can still improve. And California Department of Motor Vehicles, and they ask for AV developers to upload their, to report their any accident involved with automated vehicles on the road. And by December 2020, they received about 275 autonomous vehicle collision report. And so you can actually learn quite a bit from that, also in terms of how these vehicles are involved in into some sort of condition. So before we talk about testing autonomous vehicle, let's make some comparison in terms of how we test a human driver. When you start, when you're trying to get a driver license, you most likely will get the vision test, and you will also have a written test in terms of your knowledge related with traffic rules, and then and you will be conducting an on-road test, and someone will go with you and then ask you to drive in a naturalistic driving environment, and then give you a pass and fail. And then because we have so many drivers, and there's a lot of crash statistics has been aggregated and over the years, and so we know that roughly around 10 of 6 power of 6 miles every accident may occur, and then on average 100 million miles will have a fatal accident related with driving. And comparatively, if we're looking into autonomous vehicle, then we know that we still have that vehicle, but the driver is being replaced by automated driving system, which most likely is an AI-based driving system. And we usually use a combination of simulation and closed test track, as well as on-road test in naturalistic driving environment as well, and some of these might be a simulated naturalistic driving environment. And because we have not really deployed autonomous vehicles in a large scale, so we don't really have a lot of aggregated crash statistic yet. So with that, how to really test the autonomous vehicle? So far, there's no consensus, and there's also no standard procedure, as far as I know, how to test and evaluate autonomous vehicles. And then we know that most of the autonomous vehicles are essentially controlled by AI-based agent, artificial intelligence-based agent, and to the third-party evaluation team, this will be a black box, and that also limit the use of traditional logic-based verification and validation techniques. And so the prevailing approach to test autonomous vehicle is to utilize this so-called agent environment framework. And so basically, you have an AI-based agent, you put it into an environment, and then you look at it in terms of the situation, and then you observe in terms of what action the agent will perform, and then you evaluate in terms of their utilizing some safety metrics of that. And as I mentioned, this will be done the agent environment framework will be done in combination of simulation, test track, and then the on-road test. So this problem solve has been studied extensively by automotive engineer and artificial intelligence researchers in the past 10 years or so. As I mentioned, not a lot of transportation researchers working on this problem, but this problem indeed actually involved with transportation engineering knowledge. The reason is that because of this agent environment framework. Remember, when we talk about agent environment, when artificial intelligence researchers, when they develop the agent, this based upon some AI techniques, but when they test it, they want to utilize a naturalistic driving environment. And when we talk about naturalistic driving environment, we talk about the environment that this autonomous vehicle will be able to drive in, and that involve with infrastructure, that involve with the vehicles surrounding the autonomous vehicles, and the picture shows you such a environment. So as a transportation engineer, we study the traffic environment. We study this naturalistic driving environment in terms of the traffic flow, in terms of the traffic control devices, in terms of the multimodal transportation. So we do have a stake in it. And this problem solved indeed is also a transportation engineering problem. And my group has been working on this starting roughly about 5 years ago in 2015 and 2016. And also involved with the M-City test track construction at the time, and to test the autonomous vehicles, which we're going to talk a little bit later on in my presentation. So, I have repeatedly mentioned that the naturalistic driving environment. So what is a naturalistic driving environment? How do we model naturalistic driving environment? So I'm going to start with, say, we're going to utilize this a set of decision variables, and that decision variables involved with multiple road users. And here, let's just say all the vehicles surround the object, the subject vehicle, and also in terms of time duration. So it's not only just a number of vehicles, but also across some time duration. So from the current moment to some time into the future. And so, so then if we simulate such a naturalistic driving environment, essentially we sort of sampling this from the distribution coming from the real world traffic environment. So the challenge here to build such a naturalistic driving environment is, first of all, because the X here, the decision variables are, the dimensions of this decision variables are very, very high. And think about if you model a lot of vehicles, and at the same time, a long period of time, that your the metric will become very big. And so the number of variables will become really high. The other one is that when we say we want to test this autonomous vehicle in a naturalistic driving environment, the joint distribution need to be consistent with those from the real world. And that's also particularly challenging because of this high dimensionality with the naturalistic driving environment. And in terms of the high dimensionality, the reason we have such a high dimensionality is that because the number of scenarios and we need to test is very, very large, is innumerable. For example, you know, the sum of the variables could be static variables related with weather, number of lanes, speed limit, and configuration of the geometry. And those are all scenarios we need to consider. And also mention this dynamic variables involved with surrounding vehicles, their position and speed, range and range rate, and cutting angles and things like that. It's all the decision variables you will need to consider. And remember, this is not only just one vehicle, and there's multiple vehicles surrounding the subject vehicle on the test. There's also, you need to consider multiple maneuvers in combination of these, and some of these may be in the free flow driving situation, some of these might be in a car following situation, lane changing situation, and so the number of maneuvers need to be considered is also very, very big. So if you multiply all these together, that's no way we can enumerate the scenario, so we need to test. However, we know that the importance of the scenario are different, right? So if you just drive an autonomous vehicle on an open highway without any surrounding vehicles at night, the scenario is not very challenging to test that. Probably not going to give you a lot of information, and and a subset of scenarios which might be more important than some of these scenarios, maybe more useful to provide information related with the performance of these autonomous vehicles. So we want to be able to test these more important scenarios. So, so when we say we test autonomous vehicle, what do we mean in terms of the testing? In this case, if we want to put the agent into this naturalistic driving environment, we essentially what we're trying to estimate here is trying to estimate the probability of an accident occurs, right? So the A represent the event of interest, which in this case is an accident, and we're trying to estimate the probability of that to happen. And then, and that we can decompose that into the product of two probabilities. One is the probability of the scenario occur, so that's the PX. And then under that scenario, the probability of an accident occur, which is the PA given X. Okay, so so if we put this into the naturalistic driving environment, and if we conduct n test, and out of this n test, then if we have m of these tests, which will result into an accident, then the probability of accident occur will become m divided by n, right? So then that's the probability we're trying to estimate. The challenge here is that the accident, which the event of interest we are interested in, is usually a rare event. Okay, so as I mentioned, it's 10 to the minus 6 for accident to occur, 10 to the minus 10 to the 8, the power of 8 for miles for a fatal accident to occur. So A is a rare event, and so that brings challenge to the estimation of this probability of accident. The reason that this will be challenging is that the efficiency to conduct this test will be very very bad to do it naively. So if you want to basically to estimate the accident rate in terms of m divided by n, and if we just utilize some simple math to calculate in terms of how much how much accident you have to see to give you sort of unbiased estimate of this, then what you have here is that, let's say if you if you look at the relative halfway of this, and say 20% of that, and if you have a day of roughly the standard error, let's say that's somewhere around 2, and 2 divided by 0.2, that's 10. And because m, there's a square root of m, so in order to get m, so it's the power of 2. So 10 is the power of 2, that's 100, right? So meaning that I roughly need to see about 100 accidents. And if one accident on average is 10 to the power of 8, then that's give me 10 to the power of 10. So that's basically hundreds of billions of miles need to be run to get the unbiased estimate. So that's almost impossible for us to do so. So, so the challenge here is that because of the rareness of the event, we will need to have some better methodology to accelerate our testing. So the major challenge of this testing of autonomous vehicle in this naturalistic driving environment are two. One is the high dimensionality of this environment, and that also bring this curse of dimensionality into the picture. And on the also in addition to that, and also because of this high dimensionality of the distribution, to ensure the distribution consistency with that from the real world become more difficult to us as well. And so that's our first challenge in terms of testing autonomous vehicle in a naturalistic driving environment. The second one is the rareness of the event, and the rareness of the event also means that we need a very long mileage of testing, which is very inefficient. So these are the two major challenges we have to somehow overcome to test the AV in naturalistic driving environment. So, so I want to just propose some of our initial solutions to these two major challenges. One is obviously is the high dimensionality. So we want to exploit a spatial-temporal structure and to ensure the distributional consistency with that from the real world. So one is from the temporal perspective, we want to utilize this Markovan property, meaning that the vehicle actions at the current time step only depends upon the environment state at the current time step. The other one is that we want to exploit the spatial structure. We want to relax the spatial dependency such that the vehicle action only depend upon the surrounding vehicle rather than all of the vehicles on the road, and so that we only looking at basically a small group of vehicles surrounding the subject vehicle on their test. So that significantly reduce the number of road users or road objects we have to be concerned with. So this PX, instead of looking at all the vehicles over that much of time, a very long period of time, now I can decompose PX into two components. One is I need to initialize the initial state. So PX S0 as representing the state, 0 is the initial state. And then the second component here is related with the probability of only these surrounding vehicles. The small n over here is only concerning with the background vehicles, which might have influence on the subject vehicle on the test. And then given that, in terms of the probability of any maneuver going to be occurring with the subject vehicles. So so that basically by decomposing the PX into this, then what we can do is this PX essentially can be constructed from a large amount of these naturalistic driving data, which I'm going to show you as well. And one thing I do want to mention is when we reconstruct these from the naturalistic driving data, we want to make sure that the simulation we're going to do with this is being consistent with what we're going to observe from the naturalistic driving environment. That's not only just for this P0, which is the initial state. When we initialize, we can ensure that it's coming from the naturally, or be consistent with the naturalistic driving environment. But once you run the simulation, you want to make sure even after after some time steps, this probability is still being consistent, and that actually turns out to have some challenges to it. And then, so that's our sort of like just a very brief idea in terms of how we're going to overcome with this high dimensionality challenge. The other one is the rare event estimation challenge. So then we introduce this important sampling techniques into this. So instead of sample from PX, which is the constructed from naturalistic driving data, we sample from this QX, and QX is the importance function. And then by sample from the QX, and then to estimate this PA, then we want to basically ensure two things. One is the PA, the estimate of the accident rate by sampling from the QX, and this is still going to be a unbiased estimation. If it's not, if it's a biased estimation, then it's useless to us. So when we introduce this QX, we want to retain the property of this is unbiased estimation. The other one is that the number of required tests or the testing miles, it's need to be much smaller than this coming from the PX, right? So if it's still not reduced in terms of the number of tests needed, then that's a fail to the selection of the importance function as well. So now this the QX construction become a very important task for us. We want to ensure this is unbiased estimation. This is also can accelerate our the testing process. All right. So then come to our sort of our framework related with this naturalistic and adversarial driving environment. So all our work is based upon naturalistic driving environment, and with that, and we want to train some of these background vehicles to perform challenging maneuvers to the subject vehicle, and so to create a adversarial driving environment. So it's a combination of a naturalistic driving environment and also adversarial environment. What I mean combination is that majority of the vehicles are still following naturalistic driving rules, and then some of these background vehicles, they will be making challenging maneuvers at certain times and to the autonomous vehicle on the test. And so this obviously involves a learning process. And then what we want to ensure is to ensure that such an environment, such a naturalistic and adversarial driving environment, which we call NADE, we want to ensure the estimation is unbiased estimation. We also want to ensure we have improved efficiency to this. So now we come to this, how do we construct such an ADE that has this two property? And the theory behind this is that we find out if there exists a small subset of variables that is critical to the rare event, then we can apply the importance sampling techniques basically to construct this importance function with this small subset of variables, and while we applying essentially the crude Monte Carlo method with all the remaining variables. And by doing so, we can retain the unbiased estimation. We can also accelerate the testing process. So the idea here is that to train the background vehicles in the naturalistic driving environment to learn at what time to execute what adversary maneuvers that this will ensure the unbiasedness as well as improving efficiency. So, so the key here is to train these background vehicles. And so now it comes to how do we train these background vehicles? How do we select the background vehicles, the critical background vehicles, and select what maneuver to challenge at what time to challenge this autonomous vehicle? And that we will need to introduce another concept which we developed over the years is that to calculate the so-called maneuver criticality. So, this maneuver criticality basically involve two things. One is a maneuver which we have interest because they are challenging to the autonomous vehicle. So if it's not challenging, we're not very interested. The example I gave it to you, if it's driving on a freeway without any other vehicle surrounding you, it's probably not a very challenging situation, and it's probably not a situation we want to conduct a long test to it. The other one is this maneuver could be commonly occur, right? So if it's a maneuver that it's rarely occur in the real world, and so just to conduct such tests, it may not be very efficient as well. So it's a combination. The criticality measure is a combination of the maneuver challenge as well as the exposure frequency. So the V here, what you will see is the V, which is representing the criticality values. Basically, is looking at given the current state, what maneuvers you do, and then what is the criticality value, and that defined by a product of maneuver challenge as well as exposure frequency. The maneuver challenge is to calculate the probability of an accident to occur, and given the current state as well as given the current maneuver. And then the P, U given S is basically the exposure frequency. Given the current state, what's the probability of that maneuver will occur? So this will be, so the exposure frequency is all coming from the naturalistic driving data. And then here is that we will need to estimate in terms of what maneuver challenge we will need. And so, when we test the autonomous vehicle, because we don't, as a third-party tester, we don't really know the internal AI models they are used. So in order to estimate the maneuver challenge, here we introduced the surrogate model of automated vehicles. So what is the surrogate model? The surrogate model now is all our transportation engineering knowledge should come in play. We know that regardless of what features autonomous vehicle will have, they will need to be able to follow other vehicles. They need to be able to drive in a free flow situation. They need to be able to make the lane change. And all of these models we study extensively in transportation, particularly traffic flow literature. This also, when we construct the surrogate model, this will also bring an advantage that when we conduct a test, then once we, let's say we conduct a number of tests to this autonomous vehicles, even we don't know any autonomous AI models being utilized, and just by looking at the result of this initial test, this will give us some knowledge related with these autonomous vehicles. So some the knowledge coming from the test will help us to improve the surrogate model as well. So you essentially can build this adaptive framework utilizing some of the testing results to improve your surrogate model to make a better or make more accurate surrogate model so that you can test this in a more efficient mode. So how do we construct this surrogate model? We can utilize all the traffic flow models we have developed in terms of car following, lane changing. You can also utilize some data-driven method to construct this surrogate model. The other thing is, given that's the surrogate model, we also want to be able to estimate in terms of the maneuver challenge, right? So the maneuver challenge here is that think about in the example situation here. In this case, it's a very simple car following situation, right? So what we want to know is that what maneuver this green vehicle, which is the subject, which is the background vehicle, and what maneuver this green vehicle will do, then it will challenge the subject vehicle, which is the blue vehicle. And remember, the result of the maneuver challenge may not be the immediate next step, right? So it might involve a step that result into the future challenge. For example, if I do a lane change and from other lanes, and that may result some challenge in the future time steps. It's not immediate yet to the subject vehicle. So this involved with sort of like in the AlphaGo type of setting, you want to have they will have a value network, so they want to estimate in terms of or predict my current steps, where I'm going to put my guess on, and then to estimate in terms of the influence to my future result. So so that's why here we introduce because this is multi-step to predict this ahead. Then we introduce this reinforcement learning framework, and then to train these models to calculate, to estimate the maneuver challenge faster. So because this is we're looking ahead several steps in terms of what will be the maneuver challenge at the end of that, and it's difficult to use the traditional technique to do so. So that's why we utilize this reinforcement learning framework to estimate or to predict the maneuver challenge. Okay, so now we know how we, for each of the background vehicles we have surrounding the subject vehicle, then we estimate in terms of their, from the naturalistic driving data, we can estimate their exposure frequency. We can also predict their maneuver challenge. And then for each of these background vehicles, we need to calculate every possible maneuvers, right? So once we calculate every possible maneuver, we add up all together. Then we can calculate the criticality values for each of the vehicles, and then we select those vehicles who has the highest criticality value, and that vehicle we usually call it as a principal other vehicle. Basically, it's the background vehicle will have the highest influence to the subject vehicle at the current moment. So if once we identify the principal other vehicle, and if it is greater than certain threshold, then we will have a POV which will be able to perform certain maneuvers, will be able to challenge this autonomous vehicle. So once we had identified POV, that moment become a critical moment, and then we also know it from the criticality value. We also know which maneuver does POV will perform to challenge the autonomous vehicle. So now we can construct this importance function. So the QX function, which is the importance function, will have two portions. One is related with this POV, which basically tells us the probability of given current state, given and perform what critical maneuvers, and the probability of getting into certain accident. And then for the rest of the vehicles, for all of the rest of the vehicles, they will still follow naturalistic driving distribution. Okay, and to ensure our sampling not getting into the local minimum, And then so what we do is that we also apply what we call defensive importance sampling method. So so instead of just looking at the QX, we also explore a little bit in terms of naturalistic driving environment. So the defensive importance sampling basically involve both the QX function as well as the naturalistic driving environment. So basically, we want to explore explore the naturalistic driving environment, but also exploit the importance function. Okay, so with that, so the overall flowchart in terms of this NADE framework is we need to initialize a naturalistic driving environment, and then at every time step, we need to calculate basically observe the vehicle state to calculate exposure frequency and for every vehicle. And then we calculate the maneuver challenge, and then from that we calculate criticality value, and then we see whether it's satisfied with certain threshold, and if it does, then it's become a POV, and then that POV will perform that maneuver to challenge the autonomous vehicle. If it's not, then we'll basically for all of the other vehicles, basically to determine their maneuvers from their naturalistic driving distribution, and then we perform the next time step. So you can see basically if you have a loop in a test track, what you will do is you have an autonomous vehicle model, and you're driving on a test track, let's say a loop, and then basically we can generate all sorts of challenging scenarios to challenge this autonomous vehicle, and the autonomous vehicle can continuously to run in this environment, and eventually we'll be able to get the result. So so I want to present some of our initial work, result out of this, and the database we have been utilized is from two databases. This is all coming from University of Michigan's Transportation Research Institute. OMTRI over the years has accumulated a large amount of data. And there's two data sets specifically we're using in this study. One is from safety pilot model deployment. This is the first, basically the first connected vehicle deployment project funded by US DOT. At the time, we installed about 2,800 personal vehicles, and out of these 2,800 vehicles, 140 of these has equipped with mobile eye and also the data acquisition systems. And so there's a lot of data is being accumulated from the safety pilot model deployment project. The other one is conducted in the 1990s. OMTRI conducted a test on integrated vehicle-based safety system, and for each of the vehicles, they install a bunch of sensors. And these are all Honda vehicles and Honda Accord, and we have 100 some drivers rotate to drive these vehicles, and then there's also a data acquisition system to record everything occurs on these vehicles. So these are the two naturalistic driving database we have been using. And just to give you an example, the data we processed, and this is coming from the safety pilot model deployment project and coming from the mobile eye data. And so they will be able to detect in terms of landmarking. They're also going to be able to generate the bounding box and estimate the object distance, roughly estimated. And so we'll be able to identify when these vehicles making the lane change. So we categorize the vehicle maneuvers simply into 6 different scenarios. There's free driving, there's car falling, there's car cut-in scenarios, there's lane change with no adjacent vehicle, lane change with one adjacent, 2 adjacent vehicle, and things like that. And then with these, we will calculate the frequency exposure frequency out of that. This is just a sample of these, and we're looking at the different type of measures we will have. We're looking at the acceleration, the velocity, and things like that. And then given all the vehicle state they are in, we're calculating the distribution of these maneuvers. And then from that, we want to apply to generate this naturalistic driving environment. To illustrate this, I'm just going to give you two examples. One is a simple cutting example, which is easier for us to illustrate. The other one is a continuous driving environment. So the cutting example I'm going to illustrate is very simple. If you look into connected automated vehicle, this sort of yellow vehicle and the blue vehicle and the background vehicle, we're only concerned about the moment of the cut in. And so there's two variables we are concerning. One is the range between two vehicles, and the range rate, which is the relative velocity between these two vehicles. And the reason we utilize that to simplify this is because two dimension way easier for us to visualize. And the surrogate model we use is the Gibbs car following model. So that's the standard car following model in it's a well-known car following model in traffic flow literature, and that's the equations we utilize. And then these are the parameters, and all of that you can check from the paper. And then this is coming from the safety pilot model deployment. And so that shows you that's the data set we utilize. On the right-hand side, this is the exposure frequency. So basically, we look at all the cut-ins. This has roughly about 400,000 of these from the data sets. And then you just look at the moment they are doing the cut-in and looking at the range and range rate, and look at the frequency of that. And then so this will give you sort of like a exposure frequency on the right-hand side. And then for if you do a naive naturalistic driving environment sampling, you sample from this data, basically this data set to do the test. And what we do is we look at in terms of, for the specific situation, we'll also calculate in terms of maneuver challenge, applying that Gibbs car following model. You can see this is only on this, the small state will create challenging scenarios. And then so you multiply these together, this will give you sort of like scenario library. And then you basically only sample from the selected scenario library, and then that will significantly speed up your testing process. So we test these in not only in the simulation but also in the test track. And so as I mentioned before, University of Michigan has an MCD test facility. So what we do is we have a real automated driving system. This is the Lincoln MKZ from MCD. And then this vehicle will be driving within the MCD test facility. And in parallel, we run a simulation. And the simulation model, which is the VSIM simulation, and the simulation model will generate background vehicles, and the background vehicle will be packaged into basic safety message. We send it to roadside unit and broadcast within the MCD facility, and then the Lincoln will be able to receive that. And then, so although the Lincoln is a vehicle is only driving in the empty environment, it looks like they are driving in a naturalistic driving environment. Okay, so this is actually a video I want to just briefly show you. On your right-hand side, it's essentially is the simulation. You can see this is the Lincoln driving within the MCD on only the highway stretch. And for this particular situation, this is the subject vehicle, and then this the red vehicle is the background vehicles cut into it. The previous case is a no crash, and this one is a near miss situation, and shows you the range and range rate, and so you can see they're getting very close. And then another scenario of this is the crash situation, and you can see this is a subject vehicle under test, and there's another, background vehicle doing the cut-in. And then, although we only concern the cut-in moment, right? So just to simplify this. But the naturalistic and adversarial driving environment can run this continuously. And then they can generate not only the cut-in situation, but also the lane change and all sorts of other conflicting scenarios. So as I mentioned, we do have a continuous highway driving environment built upon this naturalistic driving environment, and we built two AV models. One is based upon the intelligent driver model, and then the mobile lane change model. And the other one is we trained by utilizing a deep reinforcement learning techniques and by ourselves. And then the surrogate model we use is this IDM plus mobile and calibrated by naturalistic driving data. And so the AV1 utilize the same model, but they utilize different parameters just to to do the test. So I'm going to show you a couple of these. Let me see. I'm going to show you some of these adversarial examples coming from these tests. So the blue vehicle is the subject vehicle under test, and all of these green vehicles are background vehicles. The one, if you see a red box, that's being identified as a POV, and the POV will conduct certain maneuvers to challenge this autonomous vehicle. You can see the first example that result into a crash situation. So this is a sort of a link conflict situation. This is another scenario. This is another in the car falling situation and result into a crash. Okay, so that's another these challenging examples which result at the end result into the crash. Result into a crash, and so so in terms of the accuracy and the efficiency, and we tested all both models, and in the simulation model we utilized, and then I can say that this is the result from the first model, the AV1 model. If you test this naively in a naturalistic driving environment, compare that to a naturalistic and adversarial driving environment, basically is 500 times faster than that, given the same accuracy. And then for the AV2 model, it's even more, even faster, and so the acceleration rate is, like 6,000 times, achieving the same accuracy. So, and we also verify in terms of in the highway scenarios what type of accident will occur, and these are the these are different type of accident will occur in the naturalistic driving environment, and we verify that with the naturalistic and adversarial driving environment as well, and you can see there in terms of the number of accident and the accident rate occurs in the NADE comparatively to NDE, they are very similar as well. So with that, I present in terms of this AV testing problem, and particularly their relationship to the transportation engineering field, and I also present some of our initial solutions to it. By no means this is the end story or a complete solution to it, and there's still a lot of work on these. We are also continuing to explore further on those. And so if you like to know, since I present pretty fast, and if you like to know some of the details, I will invite you to look at some of the papers we have published in the last year. There's the first three is what we published in IEEE transaction, and this is related with simple scenario generation utilizing the maneuver challenge, which maneuver criticality concept we developed. And then the fourth one is actually putting into a test track, not only in simulation, but can apply this technique in a test track situation. And the latest one is in nature communication, which is illustration of this naturalistic and adversarial driving environment. So this will be my last slide, and I want to acknowledge the work from my collaborators, mostly coming from they are from my research group. Some of the students and postdoc, they are really the one who are doing the work, and I've been fortunate enough in the last few years working with an excellent group of graduate students and postdocs, and they did all the work, so I'm just presenting it. And this work also being sponsored by the UTC Direct, and as well as USDOT and University of Michigan City Research Organization, and as well as DD. So with that, I think I have a few minutes left over, and I will welcome any questions. Thank you.
Thank you, Dr. Liu. A very inspiring talk. And from the audience, thank you for being with us. Do you have any questions? Please feel free to unmute yourself and speak out, or you can also leave messages in the chat box.
Hi, Dr. Liu. This is Tom, and it's really nice presentation. So I have a quick question. So based on my understanding, so you extract the driving maneuver distribution from real traffic data. So with this distribution, you build up the naturalistic driving environment for AV testing. So since the driving maneuver distribution may vary from different data sets, may vary from data set to data set. So I'm just wondering whether this difference will impact the testing performance. So for example, in one data set, one type of driving maneuver may miss, whether it will impact the final testing performance.
Yeah. So you want to classify these into different type of situations. In our case, for the work we demonstrated in the paper, right now we're only looking at highway scenarios. So you can see we did not really test any urban scenarios with intersections and these unprotected left turns and things like that. And so with highway scenarios, supposedly. You want to be that's the part of your naturalistic driving data. You want to be large enough to cover all of these different situations. So that you want to have a large enough data set. So the small data set definitely doesn't work. This one does require a large amount of naturalistic driving data.
Okay, I see. Thank you.
Sure.
Hello, Henry. How are you?
Yeah. Hey, finally, I see you.
Good to see you. Nice presentation, and congratulations on the high impact publication on this topic. I just have one question is, you apply some method to reduce the dimension of, the different scenario parameters, right? And so then you come up with some kind of critical scenarios and try to evaluate that. I was wondering, are those more focused on how they will impact the regular vehicles, or because some of the parameters will also affect the performance of automated vehicles? For example, maybe the weather or some interference of the communication, etc. So would that be included in this in this library or not?
No, so okay, so right now we're not exploring different ODDs, different operational design domain. Basically, all the static parameter we didn't consider, and all the static parameter, basically the number of lanes, those type of situations is we assume to be given. So we only consider what is the dynamic parameters, which in this case is we're assuming there's one vehicle, which is a subject vehicle on the test. And there was a bunch of surrounding vehicles, the background vehicles, and these background vehicles will perform these sort of challenging maneuvers to challenge this subject vehicle. So we did not consider the weather condition and all of that. We assume that being covered by the naturalistic driving data sets. So they should cover all the the one we have is all weather conditions, right? So we put it all together, and that's all we put it basically bundle all these together already in the naturalistic driving data.
So you assume that because you get all those maneuvers, you assume that some maneuvers could be triggered by something else, but you do not go further into what were the triggers, but you just focus on the maneuvers from the vehicles.
Right. We basically focus on the maneuvers of the surrounding vehicle, and those maneuvers will create a challenge scenario according to the naturalistic driving distribution.
I see. Mm-hmm. Yeah, the last question is, you mentioned the weather, so I'm still curious where the weather. I know that the technologies of automated vehicles, especially their sensing systems, are developing and improving. So will the weather still be kind of a challenge, or especially some adverse weather will still be challenge for the automated vehicle performance?
Oh, I mean, I think it's going to be still going to be a significant challenge. And as you all know, that the autonomous vehicle has perception, prediction, and then planning and then control. So the weather will create difficulty in all of these modules. Perception module will create a difficulty. Your planning module will have difficulty as well, and then your control module. So weather is still a very significant factor into it. Although right now in our work, weather is not being considered. It's just it's still as I mentioned, this is right now at the moment it's still a framework, and there's a lot of, for example, we need to extend this into urban scenarios, right? So and then extend this into different type of weather scenarios. And one thing I do want to mention is that we test this in the test track only in M-City, which is a small test track, has a very small stretch of freeway. And we are currently implementing this in American Center for Mobility, which is a much larger test track. And so that we'll have more scenarios to consider. And so a lot of future work still need to be done.
Sure. Thank you so much.
Thank you.
Thanks. Any other questions? I have learned a lot, and I was actually honestly very fascinated by the idea of testing, sort of giving autonomous vehicles driver's licenses the first time I heard it. So it's really a very innovative research direction, and I'm very look forward to the development of this thread of the research. So I think when we think about drivers, our human beings driving capabilities, I think we have both sensing and control. so are autonomous vehicles. So some of the errors could be from sensing, and some of the errors could be from the control. Have you seen any like report about how many of the errors are from sensing, and I mean the incidents are associated with sensing errors, and how many are with the control? And I see from your work here, it's pretty much about the control, and assuming that sensing is perfect, right?
Exactly. So that's a very good question. Some of the initial accident I have observed, and some of these coming from the California DMA, some of these actually from China. I think it's I don't really remember. I believe 2019 Beijing has a report looking at different. The error occurs because of the decision making, or because of the perception. Somewhere around 70% is actually from the perception. 30% is probably from the decision making. So both has possibilities that have problems, but a lot of these problems actually coming from the perception comparatively to the decision making. And so obviously testing of the perception model is also very important. And we also have done some work on the perception model testing as well, basically generating adversarial perception messages of data to the autonomous vehicle as well. So we're doing some of these work, although we are not at the point to present yet. It's still at the very beginning of this. So
Great.
This work is focusing only on the planning portion of it. It's on the decision making, not on the not on the perception.
Great. Yeah. So, thank you. Any other questions from the audience? I see. Actually, yeah, Christina. She's a lady running the presentation seminar platform, is asking, could we get a copy of this presentation?
Yeah, sure. Yeah, I can send that to you. No problem.
Right. Thanks a lot.
No problem.
Yeah. Any other questions? If not, I think I'll just ask